wanted to talk about some situations where 4-wire designs can be used rather than 2-wire designs. Now, most of the people who do troubleshooting across the board in electronics think 4-wire design is only applicable when we're trying to measure very small resistances with an ohm meter. So I'll attack that first. So let's think about how we measure resistance. Well, we take our leads from the ohm meter and apply them to the unknown resistor. If that resistor is many thousands of ohms, the resistance in the leads, or more importantly maybe the connections, generally banana, and probed, have resistance that becomes significant. In any event, these two R's are the total resistance from the internal electronics in the ohm meter through the connection, through the lead, and then through the connection to the unknown resistor. And because resistors in series add, the ohm meter will indicate this sum of all of these resistances. So if this resistance is very low, or if there's a need for high accuracy, where these resistances become significant, we need to somehow get rid of them. Maybe put the resistor right in the ohm meter, which is sometimes not feasible. So let's look at what happens when we use an ohm meter. Internally, this is an ohm meter, but this is inside the ohm meter. We have a voltmeter and a current source. The voltmeter reads the sum of the voltage drop across these resistances. Voltage drop only occurs when current flows. So we have to have a current source to force a current through this so that the voltmeter can react. And then the voltmeter ammeter in the digital world does an Ohm's law calculation and gets you the resistance. I'm going to start out with an analog meter. So here's a typical analog meter. Now this thing is a current meter. The current flowing through these leads causes this to deflect. Well, the leads are open right now. Put it in the ohms position, and there is no current flowing. Well, that makes sense. I can use this calibration knob though. Okay, now we have current flowing. I turn this knob until I get exactly 0 ohms. Now the advantage of this meter is the resistance of the leads is not zeroed out. See, it doesn't, there we go. So this current, and you see the variations caused by bad connections here. I'm reading 0 ohms with the leads in circuit. Now how much current does it use? Well, let's take a look. Well, the analog ohm meter reads about 2 ohms and 135 milliamps. Now this is on the times 1 ohms. Let's go to the times 10 ohms. and it reads 14.7. As the resistance increases, we don't need as much current to produce a given voltage drop. So down here's 152 microamps, and I don't know if we can read times 10, rather 63 microamps. I have a 100K potentiometer. I've set it to 0. I in fact zeroed out any of the lead resistances. The internal resistance of the milliammeter, I can do all that when I zero this. Sorry, we're drawing 153 microamps, and we turn the pot down. And you see the current drops, which it has to. This is a current meter. And I'll go up to 100, a full scale, which is 100K. Current's falling down. Meter reads 100K. So that's easy enough to understand. After all, at its very heart, this is a current meter. Current flowing through the coils in the meter, acting against permanent magnet, causes it to deflect. I'm going to zoom in on the ohms portion of this dial. I've handled dozens of different makes of analog meters since the 50s. The Simpson series, the triplet series. And this ohms switch with a multiplier is typical. And this 1 times 10 times 100K times 10. This is the only time I have ever in my life seen the maximum current flow through the unknown resistor indicated. I've never seen these markings on any other analog meter. For some reason, there's no marking of the current flow at the 10,000 times setting. Well, let's get rid of the analog meter. Here we have a DMM that's not auto-ranging. So I'm on the direct reading 200 scale. And there's 0.34 milliamps flowing from the meter through. Now it's interesting, the internal resistance is about 3 ohms. That is to say, the resistance of all the connections and the internal resistance is about 3 ohms here. Anyway, 3 ohms from this meter requires 0.34 milliamps. So it's a much lower current because this meter is much more sensitive. If I go to 2000 ohm full scale, the current drops a little bit. We still have 3 ohms. And at 20K, I think I have to change to microamps. So we now have a current of 49 microamps, 5.4 microamps. And we're probably down as low as we can go here. Anyway, the current gets lower and lower as the resistance scale gets higher and higher. So, believe me, there is some current flowing, I just can't measure it. Let's put our 100K potentiometer back in the circuit. And you can see it at 0 ohms, which shows a tenth of an ohm here. That's our current. and that as I increase the resistance, the current falls off. So we have the same thing, a current flowing through the leads that varies with resistance. What if we could do this? Let the current flow through the test leads, through the resistor, back through the test leads. And then just measure the voltage using 2 additional wires directly across the unknown resistor. Now we're not reading the sum of the resistances. We're reading the voltage across this resistor only. Hence 4 wires. 2 wires connected here and 2 wires connected here. So our voltage reading does not include the resistance of the wires. In other words, it looks like this. So the current needed to create the voltage drop, it still flows this way. Okay. And that does take some current. However, the measurement of voltage involves very, very little current. So while there's some current flowing on this wire, there's almost no current flowing on this wire. So while these drops may be significant compared to this, these drops are insignificant because the current is much smaller. Let's suppose I have a length of wire. I marked it here and here just randomly. I have no idea. And let's see what the resistance is from here to here. And you see how I cannot do it. So it jumps all over the place. It's definitely lower as they get closer and closer together. But I can't really tell anything. So let me apply some current to this wire. At 1 amp flowing through this wire from a bench power supply. And I'm using an analog meter, but it says 1 amp. If I set this on volts, see, the measurement's no longer jumping around. It's 60 millivolts. 59.7 millivolts. Well, with 1 amp flowing through the wire, use Ohm's law, and you'll see that's 60 milliohms. I go about halfway, it's 30 milliohms. So I'm reading a voltage. So this is exactly what we're doing. A known current and 1 amp or 10 amp or whatever is nice for Ohm's law, and a voltmeter. And we can measure really low ohms, as low as our voltmeter will read. And there's 18 millivolts. So that's 18 milliohms. So that's 4 wires. Count them. 1, 2, 3, 4. If this were a resistor, we would just put these leads very close together. Preferably one on top of the other if we could. But we can also measure a resistance with the exciting current some distance apart. Now, when you do this, you have to be careful not to use enough current to cause this to heat up. Device you're measuring, whether it's a piece of wire or a resistor or whatever, may change resistance with temperature. Now 1 amp through 60 milliohms is an insignificant amount of heat. See, I can lay my fingers on it all day. So if you're reading something that's a higher resistance, or even a small resistance is very, very small package, has very little heat dissipation, you have to limit the current.